Imagine boarding a flight in New York, stepping onto a sleek, futuristic aircraft that promises to take you across the globe in record time, and landing in Tokyo before your coffee cools, with the sun still rising over the horizon. Picture a world where continents are mere hours apart, where the vastness of our planet feels smaller, more connected. Imagine business trips that no longer require days of travel, but instead just a few hours, allowing you to attend meetings on one side of the world and return home the same day. This is the promise of hypersonic travel, a revolutionary technology poised to redefine our relationship with distance and time, making the impossible possible. Traveling at speeds exceeding Mach 5, 5 times the speed of sound, hypersonic flight is not just about speed, it's about transforming how we experience the world. For decades, the concept of hypersonic travel has captivated our imaginations, inspiring engineers, scientists, and dreamers alike. It represents the ultimate frontier of aviation, a bold leap into the future of human mobility. It's a testament to human ingenuity, our relentless pursuit of innovation, and our desire to push the boundaries of what's possible. The allure of hypersonic travel extends far beyond mere speed. It's about creating new opportunities, new connections, and a new way of life. It holds the potential to revolutionize global transportation, making the world more accessible than ever before. Imagine connecting distant corners of the world with unprecedented ease and efficiency, shrinking the globe in ways we've only dreamed of. The possibilities are endless. Rapid response to humanitarian crises, delivering aid to remote areas in hours instead of days, seamless international trade, and unparalleled access to cultural exchange, bringing people and ideas closer together. Hypersonic travel could usher in a new era of interconnectedness, where borders blur and collaboration thrives. It has the power to foster understanding, cooperation, and innovation on a global scale, bridging gaps between nations and cultures. However, this dream of hypersonic flight is not without its challenges. The road to achieving such speeds is fraught with technical and logistical hurdles. The pursuit of such extreme speeds presents formidable engineering obstacles, from managing the intense heat generated at hypersonic velocities to developing materials and systems capable of withstanding the immense pressures of such rapid travel. Propulsion systems must be designed to sustain these speeds, pushing the limits of current technology and innovation. Yet despite these challenges, the potential rewards are too great to ignore. The dream of hypersonic travel continues to drive us forward. It's a testament to our innate desire to explore, to innovate, and to transcend the limitations of our world, reaching for the stars. The journey toward hypersonic travel is not just about speed, it's about redefining what's possible and reshaping the future of humanity. It is a journey that has already begun, with each breakthrough bringing us closer to a world where hypersonic travel is a reality. And as we look to the horizon, the impact of this technology on our future is sure to be profound, transforming the way we live, work, and connect. The seeds of hypersonic ambition were sown in the crucible of the Cold War, a period defined by ideological rivalry and technological one-upmanship. It was a time when the world's superpowers, the United States and the Soviet Union, sought to outpace each other in every conceivable domain, from nuclear arsenals to space exploration. This intense competition spurred rapid advancements in science and engineering, as both nations sought to gain a strategic edge. The race to develop faster, more maneuverable aircraft capable of delivering payloads across vast distances at unprecedented speeds became a cornerstone of this technological rivalry. The dream of hypersonic flight was not merely about speed, it was about redefining the limits of what was possible in aviation and defense. Engineers and scientists worked tirelessly to push the boundaries of aerodynamics, propulsion, and materials science. Early experiments with rocket-powered aircraft like the German V-2 rocket and the American X-1 were pivotal. The V-2, developed during World War II, was the first long-range guided ballistic missile, while the X-1 became the first aircraft to break the sound barrier. These groundbreaking achievements laid the groundwork for later breakthroughs in hypersonic technology, inspiring a generation of scientists to dream bigger and aim higher. The space race further intensified this pursuit of speed. The quest to reach the stars was not just a scientific endeavor, it was a demonstration of national power and technological prowess. As the United States and the Soviet Union vied for dominance in space, hypersonic flight became intrinsically linked to the development of intercontinental ballistic missiles, or ICBMs. These missiles, capable of traveling at hypersonic speeds, redefined the nature of global warfare. The quest to achieve orbital velocity pushed the limits of engineering and physics as scientists sought to harness the immense power required to break free from Earth's gravity. The technologies developed during this era, from advanced materials capable of withstanding extreme temperatures to innovative propulsion systems, would prove instrumental in shaping the future of hypersonic travel and weaponry. These advancements laid the foundation for modern hypersonic systems, which continue to evolve at a rapid pace. The lessons learned from early experiments remain relevant, guiding today's engineers as they tackle new challenges. The Cold War may be over, but the pursuit of hypersonic technology continues to be a major strategic objective for nations around the world. The race has shifted from ideological rivalry to a competition for technological dominance. Hypersonic missiles, capable of evading traditional defense systems due to their sheer speed and maneuverability, represent a new frontier in military strategy. Their ability to travel at speeds exceeding Mach 5 makes them nearly impossible to intercept. These weapons have emerged as a game-changer in modern warfare, forcing nations to rethink their defense strategies and invest heavily in counter-hypersonic technologies. The ability to strike targets anywhere in the world with incredible precision and speed has significant implications for global security and strategic balance. Hypersonic technology is not just about military applications, it also holds the potential to revolutionize civilian aerospace travel. As nations continue to invest in hypersonic research, the world watches closely, knowing that the next breakthrough could reshape the geopolitical landscape and redefine the future of warfare and transportation. The quest for hypersonic flight reached a pivotal milestone in the 1960s with the development of the X-15, a rocket-powered experimental aircraft that shattered speed and altitude records. Piloted by legendary test pilots, the X-15 soared to the edge of space, reaching speeds of over Mach 6, 6 times the speed of sound. This groundbreaking aircraft provided invaluable data on hypersonic aerodynamics, thermal management, and the physiological effects of high-speed flight. The X-15 was more than just a technological marvel, it was a symbol of human ambition and our relentless pursuit of pushing the boundaries of what's possible. It paved the way for future generations of engineers and scientists to dream bigger and bolder, inspiring them to tackle the immense challenges of hypersonic flight. The legacy of the X-15 extends far beyond its record-breaking flights. The data collected from these daring missions proved invaluable in advancing our understanding of hypersonic flight and informed the development of subsequent hypersonic vehicles, including the Space Shuttle program. The X-15 stands as a testament to the power of human ingenuity and the importance of bold experimentation in pushing the boundaries of science and technology. Hypersonic flight is a delicate dance with the extremes. It pushes the boundaries of what is physically possible, challenging our understanding of aerodynamics, materials, science, and engineering. At these speeds, every element of design and performance must be reimagined to survive the unforgiving environment. At speeds exceeding Mach 5, the very air around the aircraft transforms from a benign medium into a scorching inferno. The air itself becomes a formidable adversary, compressing and heating to levels that can destroy conventional aircraft in moments. Friction generates intense heat, enough to melt conventional aircraft materials. This heat is not just a byproduct, it is a fundamental challenge that must be addressed to ensure the survival of the vehicle. Meanwhile, shock waves create extreme pressure differentials that test the structural integrity of even the most robust designs. These forces can cause catastrophic failure if not carefully managed. Overcoming these challenges is paramount to achieving safe and reliable hypersonic flight. Engineers must innovate at every level, from materials to propulsion systems, to make this vision a reality. One of the most significant obstacles in hypersonic flight is managing the intense heat generated by air resistance. This heat is not uniform. It concentrates on specific areas, such as the leading edges and nose of the aircraft, requiring targeted solutions. At hypersonic speeds, the air molecules in front of the aircraft are compressed so rapidly that they heat up dramatically. This phenomenon, known as aerodynamic heating, is a critical factor in hypersonic design. The result is a searing shock wave that envelops the vehicle, creating a barrier of heat and pressure that must be overcome for sustained flight. This aerodynamic heating can reach thousands of degrees Fahrenheit, enough to melt even the most advanced metal alloys. Traditional materials simply cannot withstand these conditions. To withstand these extreme temperatures, engineers are developing innovative materials like ceramic composites and refractory metals. These materials are designed to endure the intense heat without losing their structural integrity. These advanced materials are not just heat-resistant, they are also lightweight and durable, making them ideal for the unique demands of hypersonic flight. Another challenge lies in controlling the flow of air around the aircraft at hypersonic speeds. The behavior of air changes dramatically at these velocities, requiring new approaches to aerodynamic design. Traditional aerodynamic principles break down at these extreme velocities. The air becomes unstable, leading to unpredictable and potentially dangerous flight characteristics. Engineers are exploring novel design concepts to address these challenges. From advanced computational simulations to rapid prototyping, every aspect of hypersonic flight is being re-examined. One promising avenue is the development of scramjet engines and waverider configurations. These technologies are specifically designed to operate efficiently at hypersonic speeds. By combining innovative propulsion systems with cutting-edge materials and aerodynamic designs, engineers aim to achieve stable and controllable flight at hypersonic speeds. These cutting-edge technologies are paving the way for a new generation of hypersonic vehicles. They represent the culmination of decades of research and development. Capable of navigating the extreme conditions of high-speed flight, these vehicles promise to revolutionize transportation, defense, and space exploration, opening up possibilities that were once the realm of science fiction.